In our video today, we're going to start getting familiar with the properties of two-column proofs, so where you're given a statement and a reason in order to justify something. So we're going to start with just proving equations because we're very comfortable with solving equations. We've been doing it since before we were in algebra, and we've been using a lot of these properties that we're going to see in our proofs with equations for a long time, but just may not have understood what they were called or why we were doing those. So we're going to go through today and practice with some solving multi-step equations with variables on both sides and justifying each step as we go. So as you're solving an equation, some of the things that we commonly see are the addition, subtraction, multiplication, and division properties of equality. And all that means is that if you're starting with something like an equation where you have one thing on one side of the equal sign and something on the other, if you add the same value to each side, or you subtract the same value from each side, or multiply or divide, then that means you are keeping the equation still equal. So when you do it on each side of the equation, it is still equal. Therefore, you're not hurting the equation at all, you're not unbalancing it. All you're doing is just moving parts around and keeping things balanced in order to get your variable by itself and get a solution for the answer. So those were four properties that were commonly used when you've been solving equations. Another property that you are familiar with is the distributive property, and that's where when we see one number or term outside of a set of parentheses and we're multiplying it and distributing it to each of the terms inside, we can rewrite it as a times b plus a times c. Another property that we see is the additive identity or the multiplicative identity. And with the identity properties, you're not changing the value of something. So whenever we add or subtract 0 to something, it stays itself. Just like when we multiply or divide by a positive 1, the object does not change. While we're going through these proofs today, I am going to be abbreviating the words property of equality with POE. It just gets a little repetitive while you're working. The important part is which of these terms are you using? Are you doing addition, subtraction, multiplication, or division property of equality? One other property that we are going to see before we get into some more geometrical proofs is the symmetrical property, or the symmetric property, excuse me. And that just means that when you have something like a equals 7, the opposite of that would just be 7 equals a. We're rewriting it in that order of changing which side of the equation comes first as we read it, and that is the symmetric property. So we will be seeing that in some of our examples. So let's go ahead and get started with this first equation that we have. We're given that 5 times the quantity 2x minus 1 equals 9x plus 2. And we're asked to prove that x equals 7. So the very first step is to write down the equation, and then we're going to take our equation and look at how we would solve that first. So the first step that we could do would be to distribute the 5 to each of those terms. So if we distribute 5, we would get 5 times 2x and 5 times negative 1. That becomes 10x minus 5, and we've done nothing on the right side. At this point now, we could subtract 9 from each side, or we could add 5 to each side. You kind of have some choices on what you might want to do. What I'm going to do is subtract 9x from each side, and that leaves me with x minus 5 equals 2. So now the very last step I need to do in order to get x by itself would be to add 5 to each side, which leaves me with x equals 7, and that's what I was trying to get down to the bottom of proving. So I've done all these normal steps that we're used to, and now what we're going to do is be able to give reasons for how we got here. So the very first reason that we had was just because that was our given equation. So when you write a reason at the beginning of every proof, it will always be given. Then to go from line 1 to line 2, all we did was distribute the 5. So we used the distributive property. So we can then say distributive property is our reason for step 2. In line 3, to go from line 2 to line 3, we subtracted 9x from each side. That is our subtraction property of equality. And then our very last step was to add 5 to each side, and that left us with x equals 7, so that last step was justified by using the addition property of equality. So we've just gone through and solved an equation as we know, and then we went back and kind of retraced our steps. How did we get to each of those parts? All you're really doing here is justifying, giving a reason for why you were able to solve each part. So let's try another one. Our next given equation is negative 2x minus 15 equals 8x minus 5. So we're ultimately trying to prove that x equals 1. So what I'm going to start with is adding 2x to each side. That way I'm getting rid of that negative coefficient. So I'll get 10x minus 5 on the right side, and then we have negative 15 over here. Now all my x's are on one side. I'm going to bring my constants over to the other side by adding 5 to each side. Once I do that, I'll be left with negative 10 equals 10x. Now my variable is being multiplied by 10. The opposite of multiplication is to divide, so we'll divide each side by positive 10. And when we do that, we're left with negative 1 equals x. Now, at some point, you might just say, hey, well, I have my answer, right? But we have one additional thing we need to do in order to finish proving what was actually asked of us, and it said that x needed to equal negative 1. And so even though they are equal no matter what here, we need to take that last line and final step and say why we're allowed to switch the order of our equation. So let's go back and justify how we were able to do each of these things. Remember what we said, the very first line should always just be a repeat of what you were given as the given information in your proof. So that first justification is just that it was given to us. To go from line 1 to line 2, we started by adding 2x to each side. So adding to each side would be the addition property of equality. Then I added 5 to each side. So again, we added to each side, so addition property of equality. At the next point, we divided by 10 on each side, so just our division property of equality. And then our final line, we just switched the order of how we saw our equation, which is our symmetric property. So we can justify that flip of the order of our equation by using that symmetric property. If you feel pretty comfortable with this, I want you to pause the video and try the last one on your own before you listen to the explanation. But if you want to hear a little bit more step by step, go ahead and keep listening. We've got negative 4 times the quantity x minus 4 plus 10 equals 8 plus x here. So on this step, remember, we always start with our given information. So this was just our given equation. So our reason for step 1 is that it was given. In our next line, we can take that negative 4 that's outside of parentheses and distribute it. So we get negative 4x plus 16, and then that plus 10 equals 8x plus 2. Nothing has really changed there. All we did was distribute that negative 4. So what we can do here is take away that negative 4 by just distributing it. So we use distributive property. To go from this line to another step is we can combine our like terms here. So notice we have a 16 and a 10 on the left side of our equation. Since they're both constants, we want to combine them before we bother doing anything else to both sides. So at this step, something you could say to justify what we just did would either be to simplify your work or that you were combining like terms. So either of those would be good reasons for how we just got our answer. So you can either write simplify or you can write combine like terms. At the next step now, I'm going to try to get all of my variables on one side and all my constants on the other. So I'm going to add 4x to each side to get rid of this negative 4x. That's going to leave me with 26 equals 12x plus 2. And so all I did there was just add 4x to each side. So that was my addition property of equality. In the next line then, what we can show is that we are going to get our constants on one side. So I'm going to subtract 2 from each side here. And that's going to get me 24 equals 12x. And because I subtracted from each side now, I use the subtraction property of equality. I'll divide each side by 12, and that leaves me with 12 equals x. Now again, we are at a solution. If we were just asked to solve this equation and not in proof form to get a certain statement, we could be done. Oops, sorry, not 12 equals x. 2 equals x, because 24 divided by 12 is 2, not 12, my mistake. We were asked to prove that x equals 2. So remember, we're really close to that, but our symmetric property allows us to flip the order of our equation. Therefore, that last reason would be using the symmetric property to get down to that final statement of proof that we needed. All right, so now that we have gotten a little bit more comfortable with some of our proofs that we're going to be writing, we're going to look at it now with how we are applying that to our geometrical proofs and geometry terms and concepts that we've already learned so far. So this year so far, we've talked about definitions of midpoint, right angles, angle bisectors, segment bisectors, what it means to be congruent versus equal, supplementary and complementary angles, as well as vertical angles and perpendicular lines. We've also seen some postulates, including the segment addition postulate and angle addition postulate. And remember that postulates are statements that do not need to be proved. So because they don't need to be proved, we can use them in a proof. So other properties that are going to be kind of new, but that we will need for our proofs are going to be these four down here. The reflexive property is just saying that whatever you have is equal to itself. Therefore, if we saw the measure of angle B equals the measure of angle B, we are just defining that something is equal to itself. And so this will come up sometimes when you need to be able to say that you're taking an equal amount from each side. We don't use this one super often, but it does end up coming up when we talk about congruent triangles. So you won't see it a whole lot now, but we will use it later on. Our transitive property of equality is if CD equals GH and GH equals RS, then we can assume that CD equals RS. Now we just finished up with our unit on conditional statements and biconditional statements, as well as the law of detachment and law of syllogism. So this transitive property rule is very similar to the law of syllogism, where we had if P then Q happens and Q then R happens, we know that the Q, it kind of connects P and R, and therefore P happens and then R will happen. So we can kind of think of transitive like the law of syllogism, but it's using our equal signs here because it's a property of equality. Our symmetric property, what we already talked about with our equations on the front. So if BC were to equal RL, we know we can rewrite that equation as RL equals BC, because if they are equal, then it does not matter which order we are writing our equation in. And then finally, we have the substitution property, and the best way I like to think about this is if we have a substitute in the classroom, that substitute comes and replaces the teacher. So it's replacing one thing. Transitive property needs two parts at least to be able to make that third statement. So substitution is kind of a big umbrella of replacing things with one another, but transitive property specifically needs these multiple parts in order to claim that last statement. So our substitution property example just shows us that if we know the measure of angle A is equal to 45 degrees, then 3 times the measure of angle A would be whatever 3 times 45 is, which gets us 135. All right, so those are some of our properties that we're going to need. So let's work on how we could start writing a proof if we were given a statement or given a diagram or both, and where we could kind of begin with that. So in this first example, it says given M is the midpoint of AB, and then it gives us this diagram where we've got a segment AB and point M is marked on it. So as soon as I read that M is the midpoint, something that I know happens is that this segment becomes congruent to this segment, because we learned that the definition of midpoint is that that midpoint kind of cuts that line in half, right? And it makes two congruent parts. So a statement in geometry that we could write now is that the segment AM is congruent to the segment MB. And if we had to justify that in a proof, we could say that that's because of the definition of midpoint. So we can use definition of something that we've learned as justification there. So that would be a good reason. The one next to it says that the line DE bisects the line AB. So DE was drawn and it cut in half the line AB. So that means that this part is cutting AB into two equal parts. Therefore, the statement that we could write is that the segment AO is congruent to the segment OB. We could also say that because of that given information, we also know that O, point O, is the midpoint of AB. You could kind of go to there. So either one of those would be valid statements to come from that. And again, the reason why we're able to say that is because we're using the definition of segment bisectors here. Because we didn't use midpoint definition on this one because midpoint wasn't explicitly stated. It specifically uses that word bisect. So we're using that definition of that word to help us make a statement. In our next statement, we are given this angle diagram, and that is all it says. Now I notice that I have angle AOC. I've got a ray OB that's kind of inside of that angle, but it doesn't necessarily bisect it because I do see that this is marked congruent, but that bottom angle does not have a marking on it. So we don't have two congruent angles, and it wasn't bisecting because there's no congruent parts or marked that are there. So all we could really say here is that we would know that the measure of angle AOB plus the measure of angle BOC would equal the total measure of angle AOC. And remember, that is just our angle addition postulate. Whenever we have two angles that are adjacent, then we can add them to get their outer angle that they share. So that is just our angle addition postulate showing up here. In our next diagram, we've got a segment. Again, it just says see the diagram. So we have a long segment MP. It's got other points on it and an O. There are no markings on this, and we weren't told anything about being bisected or given a midpoint. So the most we could really say is that we would know that MN plus NO plus OP would equal the entire length of that segment MP. So those lengths added together make that, and that is because of our segment addition postulate. So again, very similar to our angle addition postulate that we just saw, but using segments. In our next example, it says the ray OB bisects the angle AOC. So because we were specifically told in this diagram that that ray is bisecting the angle, we are able to claim that these two smaller angles inside would be congruent. So I could say that angle AOB is congruent to angle BOC. And that would be because of the definition of an angle bisector. It specifically used the word bisect, so we're relying on that word's definition to make a claim. And finally, in our last one here, it says given AB plus BC equals AC, so I can see that this chunk of this segment plus this one would equal the entire line. And we're also given that the length of AB is equal to the length of JK. So since we know that those two pieces are equal, we could rewrite the statement, and instead of saying AB plus BC equals AC, I could replace AB with JK. So I'm putting JK plus BC equals AC. So the statement that I'm now writing is this: JK plus BC equals AC, and that's because I knew that AB and JK were the same amount. It was given to us. So I did that replacement part of replacing that one item. So that was me using the substitution property. Think about like the sub for AB. Today, the substitute teacher is Miss JK. So she's coming in to replace Miss AB here. So it's a substitution property of equality. All right, so now that we've kind of taken some practice with having those information given to us, what we could say about it, let's actually apply that to some of our proofs here. So in this first proof, I'm giving you the information that I'm telling you the C is the midpoint of AB and that CB and DE are congruent. And I'm asking you to prove to me that AC would be congruent to DE. So I have a couple things. One thing that I would always recommend is mark your diagram based on what is given to you. So since I know that C is the midpoint of AB, I automatically could say that I know those two segments are congruent. I was also told that CB is congruent to DE. Now DE is down here, and I just marked CB with one tick mark. Since they also have to be congruent, I can give DE that same marking. So right away, just by marking that, I can see that now all three of these small segments are going to be the same length. So let's talk about what our reasons are in the proof of why we actually are allowed to assume that. So this first line where C is the midpoint of AB and CB and DE are congruent, that was just given to us, right? Now to go to the next line where it says AC is congruent to CB, It's taking these two parts and saying they're congruent. Well, why are we allowed to say that? Look at your line above. We were told that it was because it was a midpoint. So that means we are relying on the definition of midpoint to make that conclusion. Now to get to our last line then, we can say AC is congruent to DE. Well, why are we allowed to say that? So DE was already mentioned one other place. AC has also been mentioned. Up here, we said that AC was congruent to CB. And we said that CB and DE were congruent. So because we have A, C, and DE both being congruent to CB, we're using the transitive property here to say that, well, that means they must be congruent to each other. So because we had those two pieces of information ahead of time, we can use the transitive property of equality here. You could also use substitution property, but this is more specifically transitive property because we've had those two given statements and we're now coming to that third conclusion. We're going to try a few more proofs with these new properties that we've learned so far today. So this information says that we are given AC is equal to BD. So remember, that just means that whatever the measure of this segment is, it is the same equal amount as the measure of BD. We're going to prove that AB is equal to CD. So those two smaller pieces, we want to show that this and this are congruent, but we don't know that yet, so we can't actually mark it on the diagram at this point. So the first statement that was given matches the given information. So the reason is just given. Now when I look at the next line here, this is already filled in for us, so we read it as AB plus BC equals AC. Well, that's just saying that AB plus BC equals the whole length of the segment that it's made up of. So that would just be because of our segment addition postulate. Now when we look at our next line, we have something similar. It says BC plus CD equals BD. So it's taking BC plus CD and saying that that's equal to BD. So again, that is just our example of our segment addition postulate showing up again. So it's okay, sometimes you will have the same reason 2 lines in a row. This just happened to work out here because we needed to define both of those parts to get to our next line. What you'll notice then, the only thing that changes from this line that we just were down to here is that we have BC plus CD still, but now it's equal to something else. So we've taken BD and we've replaced it with AC. Well, why were we allowed to do that? BD was here, and we said originally it was equal to AC. So since we've now just taken that one piece and replaced it, we are using the substitution property of equality here. Now if we go to our next line, we notice that we have AB plus BC, which did already show up somewhere, and we're setting that equal to BC plus CD, which showed up in 2 other places. Now let's kind of see where that came from. We took the yellow statement was equal to green, and we said that the blue statement was also equal to green. Therefore, yellow must equal blue. So we've had 2 parts that have helped us get there. That is an example of our transitive property of equality. Now finally, all we're doing is going from this long equation down to just AB equals CD. So what changed from this line to this line? Well, we still have AB and we still have CD, but we seem to get rid of BC and BC. Well, if BC is equal to itself, we know we could subtract it from each side, and therefore it's remaining equal. We're just taking that same amount from each side. Then that would mean that all we used was the subtraction property of equality, just like we did back when we started looking at our equations to solve. All right, so we're going to go ahead down to our next proof. We are given that the angle 2 and angle 3 in the diagram are congruent. So remember, we can mark them as being congruent here. And we're asked to prove that the measure of angle 3 equals the measure of angle 6. So let's start with what we already know. Angle 2 and angle 3 are congruent because it was given. In the next line, we're jumping to angle 2 is congruent to angle 6. Looking at your diagram, 2 and 6 are across from each other on intersecting lines. So the reason that we know those are congruent is because of the definition of vertical angles. Remember, those are a vertical angle pair, and vertical angles will always be congruent. And then in our next line, we're saying that 3 and 6 are now also congruent. So use what we've seen already. We had angle 2 showing up twice, angle 3 is showing up twice, and angle 6 is showing up twice. So we had green is equal to pink, green is also equal to blue, therefore we can say pink and blue are equal. So that would just be our transitive property showing up again. Now to go from this last line that we just saw into the very final statement we want to prove, we have a difference in notation here. This says that the angle 3 is congruent to the angle 6, but we're now saying that the measure of angle 3 must be equal to the measure of angle 6. Why are we allowed to go from congruent symbols into measures being equal? Well, we're just using the definition of what it means to be congruent, right? So we're saying the definition of congruent angles would mean that if you have two congruent angles, their measures must be the same. So that's just our definition of congruent angles showing up there. All right, and our last proof for today says that given the measure of angle 1 is equal to the measure of angle 2 is equal to the measure of angle 1, and the measure of angle 3 is equal to the measure of angle 4, prove that the measure of angle ABC is equal to the measure of angle DEF. So lots of angles going on here. Let's take it one step at a time and mark our diagram with what we know. So we're originally told that the measure of angle 2 and angle 1 are going to be equal. So that means if angle 1 was 30 degrees, angle 2 would be the same exact amount. Same with our angle 3 and angle 4 having the same measures. Now they're not necessarily equal to 1 and 3 aren't the same and 2 and 4 aren't the same, but we are trying to show that A, B, and C and D, E, F are both congruent angles there. So let's take a look at our proof now. The first line, remember, is always whatever we were given, and that matches exactly as it was written, so we can say the reason for that is that it was given. In the next line, we're writing that the measure of angle 1 plus the measure of angle 3 equals the angle ABC. So we've taken those two adjacent angles and shown that when you add them together, you get their outer angles value. So that is just our angle addition postulate. If we look down at the next line, angle 2 plus angle 4 equals angle DEF. So those measures added together make their whole angles measure. So again, just using the angle addition postulate. So the reason is repeated, but that new line statement is definitely a different part. So that's why it's repeated. It's making two independent statements, but they both had the same reason there. So now let's take a look at what changes down below. We can see that we still have the measure of angle 2 plus angle 4 showing up right here. But we've gone from having the measure of angle DEF, and now we're saying that it is the measure of angle ABC. Well, why were we allowed to do that? Let's go back and take a look here. We knew that the measure of angle 2 was the same as the measure of angle 1. So 2 and 1 are allowed to be the same. So let me actually use a different color here. 2 and 1 are the same. So wherever I see a 1 or a 2, they can have the same amount. I also know that 3 and 4 have the same amount. So wherever I see a 3, I could also see a 4. So what really happened here is that we took that line 2 equation right here, and to become line 4, all we did is replace 1 with a 2, and we took 3 and replaced it with 4. So we took those individual amounts from step 1 and replaced them from 2 to make line 4. So that was just us using the substitution property, and we happened to use it 2 times. But it is still just substitution here because we took one little part and replaced it in both of those equations. Finally now, to get to our final step, let's see why we're allowed to make the final claim. The measure of angle ABC is now equal to the measure of angle DEF. So DEF is shown up here and ABC is shown up here. We made it so that they were both equal to this this expression of measure of angle 2 plus the measure of angle 4 is equal to those. So since pink is equal to blue, but pink is also equal to green, blue and green must be equal. And because we have those three parts there, that is our transitive property of equality.